We've been able to evaluate integrals that involve sine and cosine before, so this is not new information. But what is new is that every integral that we've used before has had both sine and cosine in that integral when one of them was raised to a higher power. In other words, we've had a u substitution where what was being operated on was u, and the derivative of that was definitely in there, so we could rewrite this integral equivalently as u cubed du. We've been able to do that for a while, but what we haven't been able to do up this point, because we haven't had a technique for it, is what if we just had the sine of x cubed? Well, that's not a u substitution. We haven't been able to evaluate integrals like that before. What if we had something that was cosine of x raised to the fourth power? Well, because sine of x is not inside that integral, this is not a u substitution. So we have to come up with a different technique in order to evaluate those. And so we do. There are two cases when we're evaluating an integral that involves sine raised to a power or cosine raised to a power by themselves, where their derivative function is not included in there. And those cases hinge on whether n is even or odd. The first case I want to look at is the case where n is odd, because there are completely different techniques. We have one technique for when n is odd. We have a completely different technique that we're going to use for when n is even. So let's look at an example. So the case where n is odd, sine is by itself inside this integral, cosine is nowhere to be seen, so it's not a u substitution. We need to figure out some way to manipulate this using algebra, using trigonometry, something to do to that integrand so that we stand a prayer of evaluating this integral. And it turns out we can use algebra and a trig substitution and manipulate the integrand so that we can actually integrate it. Now, some things I want to remind you of trigonometry-wise. Remember the Pythagorean identity. The sine squared of theta plus the cosine squared of theta equals 1. We can solve that for sine squared using algebra, subtracting cosine squared from both sides. We could solve that for cosine using algebra to subtract sine squared from both sides. So we're going to use this trig substitution in something that I call, when n is odd in this case, I call this the peel one off technique. And you'll see what I mean by peel one off. So I have in this integral, I have sine of x multiplied by itself 5 times. Well, what I'm going to do is I'm going to peel one of those off, because that's what this means. This means sine of x times sine of x times sine of x multiplied by itself 5 times. So I'm going to peel one of those off, and I'm going to realize, or hope anyway, that I can use this as du. Well, if du is sine of x dx, then I realize that u is going to have to be something involving cosine, right? So I need the rest of this. The reason I peeled that one off, and the reason that I highlighted this Pythagorean identity equation here, is that I can use this as a substitution every time I see sine squared. So what I'm going to do is completely rewrite sine of x to the fourth as sine of x squared. Remember, we put it before the angle measure, squared. And I'm still going to have my one that I peeled off there. And now all I have to do is every time I see sine squared of x, I get to write 1 minus cosine squared of x. Give myself some room here. So what I'm after, I haven't done any calculus yet. What I'm after is simply using substitutions to try to get myself into a position where I can use U substitution to evaluate the integral. And I'm pretty much there. Now I'm going to go ahead and FOIL this out. And so that becomes 1 minus 2 cosine squareds of x plus a cosine to the 4th of x. Hopefully you can see that. I just FOILed that out. First, outside, inside, last. And now, this is a U substitution problem. If I say U is the cosine of x, then du has to be negative sine of x dx. I know that's different than the u and du I had a while ago, but it really doesn't matter. Cosine can be negative, sine can be positive. But this is how we would normally do a U substitution problem. So everywhere that I see cosine, I'm going to write U. So this becomes 1 minus 2u squared plus u to the 4th times du, and I'm off by a negative. And now we know how to do this. This is just power rule. We have turned a single integral involving sine of x only multiplied by itself 5 times into a straightforward power rule for integrals using u and du. Here's the peel one off method. I'm forcing one of those signs to be du, and I'm going to use trig substitution to make the rest of it in terms of the antiderivative so that that can be du. I've got to put the rest of it in terms so that I can have a u that goes along with that du. So it's peeling one off and using the Pythagorean identity to turn the rest of it into the other function. So this is negative with respect to u, 2 minus 2/3 u cubed plus 1/5 u to the 5th plus c. This is an indefinite integral. Now I'm going to substitute back in terms of my original variable. So everywhere there's a u, I'm going to write cosine of x. So minus 2/3 cosine cubed of x plus 1/5 cosine to the 5th of x plus c. Now I could go ahead and distribute this negative if I wanted to, but we're not really after practicing the algebra part of it. We're after practicing the calculus part of things. So when we have sine or cosine by themselves in an integral raised to an odd power, we are going to peel one of them off and use the Pythagorean identity to substitute correctly using good algebra in terms of the other trig function so that we can use U substitution. So there's one technique. I call it the peel one off technique. All right? The other case that we're going to explore is where n is even. Now, I want you to notice something. We're going to play around this a little bit. Let's say I tried to use the peel one off method here. I want to prove to you why the peel one off method is not going to work for us. If I force this to be du, then I need u to be in terms of sine, right? So I need some sort of substitution for the cosine cubed of x to put it in terms of sine. Well, I can't, because the Pythagorean identity is based on squared values for sine and cosine. That's why it works in the peel one off method, because if we peel one off of when n is odd, what's left is even. So we get to make that substitution like we just did. But if we start out with an even n value or power value and we peel one off, what's left is an odd value, and that's not going to help us with the Pythagorean identity. So this is why we have to have a completely separate technique for when n starts out being even. And that technique falls back to those two trig substitutions that we used a lot when we were evaluating integrals when we did the area of a polar curve, where sine squared of theta and cosine squared of theta showed up a lot. So this is equivalently written the cosine squared of x squared. And so what I'm going to do is come over here, because again, I don't know how to evaluate this integral. I'm going to have to manipulate my integrand to get it into a form where I can actually evaluate it. And so I'm just going to make that straightforward substitution for cosine squared. 1/2 the quantity 1 plus cosine of 2, not theta, sorry, 2x. And that quantity gets squared because this is equivalent to what's inside that parentheses. Do you see that? So again, I have to do some algebra here. I'm going to go ahead and just square my 1/2. That becomes 1/4, and pop that thing out front. And that way I don't have to worry about distributing that fraction or anything like that. So I'm just going to square those two right there. I'm just going to FOIL those out. It's just first, outside and inside gives me 2 cosine of 2x's. And last gives me a cosine squared of the angle measure of 2x. All right? Now, there we go. Now, this is not a u substitution. I can't say that u equals the cosine of 2x, so that this is 1 plus 2u plus u squared, because there is no sine. I don't have anything for my du. Now, these terms, I'll pick up another color, these terms with respect to x, those two, I absolutely can find the antiderivative for those right now. This is a u substitution. 2x was fed into the cosine function machine, so I know how to do that. But this one is still going to give me issues. Remember, integrals, I'll take time to write this down, break up over addition and subtraction, but they break up. I'm going to pop that 2 out front. This becomes the cosine of 2x dx. And then I would have plus the integral of the cosine squared of 2x dx. And the 1/4 would get distributed all the way through. These two integrals I can find right now. That'd be 1/4. The antiderivative of 1, remember there's a 1 there, with respect to x is just x. I'll pop my 2 out front. This is a u substitution where u is 2x. Therefore, du would be 2 dx. I'm off by a constant of 1/2. So this is 1/2 the cosine of u du. So I definitely can find the antiderivative there. That is 1/2. What did I take the derivative of to get positive cosine? That was positive sine. And instead of writing u, I know right up here that u is 2x, so I'll go ahead and just put 2x in there. And there's the antiderivative of that integral. So I already know how to do that. But that gives, I have issues right here. I don't know how to find the antiderivative of that function. So look what I've got to do. If it's true that the cosine squared of theta equals 1/2 times 1 plus the cosine of the double angle measure of theta, then it doesn't matter if theta starts out being 2x. I can still use this substitution because it's cosine squared. I'm going to put 1/2 times, I'm running out of time. I'll pick this up in the next video.